Tropical rainforests and hot desert are biomes that can be found running in parallel lines across the face of our Earth. The tropical rainforest can be found running along the equator, whilst the hot desert can be found running along the tropics. But here's the real question. Why do they do that? Why do they run in parallel bands at the equator and at the tropics? Well, in today's video, we're going to find out. We're going to look at the concept of solar insolation, not insulation, and the idea of the Hadley cell. So, let's get into it. Solar insolation refers to the amount of solar energy an area receives. Solar energy being, of course, energy from the sun, hence the name solar energy. Don't know how well I can explain that. And on Earth, the amount of solar insolation varies depending on where you measure it from. If you're at latitudes that are higher or towards the poles, you tend to find that there's less solar insolation, whereas if you're towards the equator, it's much higher amounts of solar insolation. And this is because, you can see on my little handy diagram up here, that due to the curvature of the Earth, solar energy falls into a much larger area as you move up into the higher latitudes. So this means that as we move into the higher latitudes, solar energy falls onto a wider area, which means that it's less concentrated, which means that temperatures tend to be a lot lower. Whereas when we move towards the equator, solar energy falls onto a much smaller area, meaning it's more concentrated, meaning there's more energy, meaning it tends to be hotter. Kind of makes sense, doesn't it? More concentrated, hotter, less concentrated, less hot. Pretty simple. Here you go. Here's a little experiment to kind of showcase this at home. And all you need to do this experiment is a ball and a torch. And as you can see from my slightly more elaborate setup, we have big budget money here at Mr.ThomasTheTeacher because I've also got some tin foil and a plastic tube. And that's simply just because I used it to block out light. You don't actually need that to do this experiment. It's just better for the camera. As you can see, when my torch is pointed at the equator of the Great Ball, you can see that the light is a lot more concentrated. It's spread over a much smaller area. It's kind of focused in on a single point, which is the exact same as it is on Earth. As we move towards the equator, energy is more concentrated, and that's why the equator tends to be a much hotter region of the Earth. Then, as I move the torch upwards, you can see that the light becomes a lot less concentrated. It diffuses outwards. The size of the tube hasn't changed, the distance away from the Great Ball hasn't changed either. It's simply because of the curvature of the ball. That means that the light is being spread out over a much larger area, just as it does here on Earth. Just like the Great Ball, here on Earth, solar energy gets spread out more as you move towards the poles, hence why it's colder as you go up into those higher latitudes. So solar insolation leads to what we call differential heating here on Earth. That's where some places receive more energy than others, so they get hotter than others. And so that leads to the creation of what we call atmospheric cells. And for example, the one found at the equator, the Hadley cell. And this Hadley cell creates the conditions required for both the hot desert and the tropical rainforest to be found where they are on Earth. Firstly, solar energy at the equator creates very warm conditions, which in turn warms the air and causes it to rise. I'm getting deja vu for some reason. Weird. Then, as this hot air begins to rise because it's become less dense, all the moisture that it contains is lost through a process we call convectional rainfall. So as it goes through the atmosphere, moisture begins to come out in the form of rain. This in turn creates a hot and wet climate at the equator, which is, funnily enough, the exact climate needed for the tropical rainforest to form, and hence why we have tropical rainforests at the equator, because it's very hot and it's very wet because of this idea of convectional rainfall and solar insolation. So back to the air then. As it continues to rise, it loses all its moisture and it hits a layer in our atmosphere known as the troposphere. The troposphere acts almost like a ceiling and it prevents the air from going any further up into the atmosphere, and so it spreads both north and it spreads south. And so as the hot air moves across the troposphere, it begins to cool down. And as it cools, it becomes more dense and begins to fall towards the ground. I swear I've done this. This is really weird. And so now this cold, falling air that has no moisture in it whatsoever falls back down towards the ground at roughly 30 degrees north and 30 degrees south, right above the tropics. As this cold, dry air falls back towards the ground, it creates an area of high pressure, so clouds can't form. I mean, the air was dry to begin with anyway, so clouds are very unlikely. So basically, right above the tropics, you get these very dry, very hot conditions because there's no cloud cover to provide shade. Wait a second. Oh, hot, dry conditions. It's the world's hot deserts, which form, funnily enough, right along the tropics. Who would have guessed? Oh my god, what a surprise. I'm being very sarcastic right now. Of course you knew that, that's why I'm doing this whole video. And so, just to recap, hot deserts form because of dryness, not because of temperature. Back to the air thing. So the air, it's in an area of high pressure. It wants to move to an area of low pressure, wants to equalize. And so the nearest point of low pressure, you would have guessed it, it's the equator. And so the wind moves from the tropics back to the equator through what we call the trade winds. And this completes our Hadley cell, sometimes referred to as the intertropical convergence zone, because we've got air converging in between the tropics. And so this creates a cycle of hot, rising air and cold, falling air. Wait a second, I've definitely done... Oh, that's right. It's a convection current. It's the exact same concept that we covered in a previous video when we were looking at convection currents within the mantle. These are the exact same thing. You've got hot rising things, cold falling things. Isn't that funny that geography has this idea of interlinking things? Weird. And so that's why we find the world's hot deserts and the world's tropical rainforests along the tropics and the equator. Lovely jubbly, all because of solar insolation, the shape of our planet, and convection currents. They're going to just keep coming back. We're going to keep revisiting convection currents all the time. Can't wait. And there we have it. Well, as always, it's time for you to pack up, like the video, subscribe to the channel, find me on Tickers. There's a worksheet down in the description below, and I'll see you in the next one. Adios. So, the Earth's... Okay, nope, we're doing that wrong already. So, the Earth's tropical rainforest and the solar insolation, I said it then. Solar insolation refers to the amount of solar energy an area on Earth receives.